At the edge of the region that we are modeling lies the boundary for our volume. Call the surface area of the volume T and n hat the unit vector normal to this surface. For neutron transport, boundary conditions represent the angular flux psi that enters the volume from outside of the boundary. That is, when n hat dot omega hat is negative. In order to solve the transport equation, we need to know the angular flux right at the surface. That is, when the position vector is on T. We'll discuss 6 common types of boundary conditions. 1. Explicit boundary conditions. 2. Vacuum boundary conditions. 3. White boundary conditions. 4. Reflective boundary conditions. 5. Albedo boundary conditions. And 6. Periodic boundary conditions. Explicit boundary conditions are when the reentrant flux is a known function. Call it tilde uppercase psi. Thus, the angular flux at the surface is this known flux tilde uppercase psi. In the particular case where there is no reentrant flux, this is called a vacuum boundary condition, and in this case, our flux at the surface is just equal to 0. A white boundary condition, as in the term white noise, is when all the neutrons leaving the volume end up returning. However, when they re-enter the volume, they re-enter with an isotropic angular distribution. All the information about the direction that they left the volume with is completely lost. Symbolically, we can represent the angular flux re-entering the volume as the average of the angular flux leaving, simply smoothed out over all possible angles. In reflective boundary conditions, on the other hand, the neutron returns in the opposite direction that it left. This means that the returning direction, omega hat prime, is defined by n hat dot omega hat equals negative n hat omega hat prime. This means that the magnitude of the flux re-entering the volume is the same as the magnitude of the flux exiting the volume. Or psi of omega hat equals psi of omega hat prime. As a generalization of reflective boundary conditions, albedo boundary conditions return neutrons in the opposite direction, but scale the magnitude of the flux by some parameter alpha of E, which happens to be unitless. Therefore, the reentrant neutron flux is seen to be psi of omega hat equals alpha of E times psi of omega hat prime. A periodic boundary condition is one where the neutron reappears on the opposite side of the domain, but with the same direction and magnitude. Denoting the distance between two opposing surfaces of the volume as the vector r sub L, thus we see that the flux psi at a position r is equal to the flux psi at a position r plus the distance between the two surfaces r sub L. This applies only when the reflecting boundary repeats infinitely.